This is going to mark the end of chapter 4 and our moving on to the next pillar of geometry for following the text, um, notion of what exactly constitutes the 4 pillars of geometry. So, um, when we spoke of isometries, our notion of a rotation, right? So we defined a rotation of R2 as a function. And remember, because we wanted to avoid actually measuring angles, right? We dealt directly with the real numbers that were, we called them C and S, but they were the cosine and sine of those angles in question. So we thought about it as a function R sub CS, where C and S were 2 numbers that satisfied this fact that C squared plus S squared is equal to 1. So they satisfied this the fact that they lied on unit circle. And so this function R sub CS was described as the one that sent a point of R2, so xy, got sent by this R sub CS to Cx minus Sy in the first slot, and in the second slot it got sent to y, so y got sent to Sx plus Cy. Okay, and so we saw that this was a pretty weirdly described thing, but when we did this, we saw that not only was this an isometry, that's one of the things we proved. So this is an isometry, but also this actually was the rotation that we thought it was, right? So we actually drew a diagram to see how unit circle, for instance, was transformed by this, and it did exactly what you thought it would do here. Okay, so even if it didn't look immediately like that's what it was doing, that's exactly what it was doing. So it turns out, right? And many of you probably noticed this when you saw it, or you recognize where this came from, coming from linear algebra. So it turns out that an easier way to describe this transformation comes via matrix multiplication. So what matrix multiplication can I use here? Well, I can multiply the a vector xy. Right, so now if I'm thinking about this as being a column vector denoting my ordered pair, xy, I can multiply by this vector xy on the left by the 2 by 2 matrix C minus S, S, C. And when I do that, what do I get? Well, I get a column vector with 2 entries. So in the first slot, this is Cx minus Sy. And in the second slot, this is Sx plus Cy. And that comes directly via matrix multiplication. Okay. So here I have a 2 by 2 matrix C minus S, S, and C. But of course, if the rotation in question is about the origin through an angle of theta, then C is cosine theta, and S is sine theta. Right? Thus, the matrix that gives us rotation through an angle theta about the origin is, and what we mean by the matrix gives us is once I know the matrix, then the transformation in question is just multiplying on the left by the matrix. So this is the matrix cosine theta minus sine theta, cosine theta. Which you have probably seen before in 240 or 461, right? Any linear algebra course that you've taken, this was done. This was written out at least once as an example of a standard matrix for a transformation. So this is it. Okay. So what is the benefit of doing it this way? So one benefit is to prove angle sum formulas, right? So note we can conveniently prove angle sum formulas using this formulation. So note we can conveniently prove angle sum formulas for, say, cosine of theta sub 1 plus theta sub 2 and sine of theta sub 1 plus theta sub 2 using matrices in this way. Okay, well, I say note that, but how do I actually see that? So let's see what's going on here, right? So let's, whenever I would be doing a thing, cosine of theta plus 1 plus theta, or plus theta, or sorry, cosine of theta sub 1 plus theta sub 2, and sine of theta sub 1 plus theta sub 2. Whenever I'm doing computing with something like this, what would the associated transformation be in this matrix? Right, well, that would be the transformation that is rotation through the sum of this angle, right? The sum of these two angles. So it would be rotating theta sub 1 and then rotating in theta sub 2, right? First step, rotation through angle theta sub 1 is given by the matrix cosine of theta sub 1 minus sine theta sub 1 sine theta sub 1 cosine theta sub 1. And rotation through angle theta sub 2 is given by the same matrix where theta sub 1 has been replaced with theta sub 2. So this is given by the matrix cosine of theta sub 2 minus sine theta sub 2, sine theta sub 2, and cosine of theta sub 2. Okay. All right. Thus, the rotation through the sum of those angles is given by the product of these two matrices. So this is given by the product of these two matrices. Okay, so then we can multiply them together. Let me copy these real quick. I have cosine theta sub 1 minus sine theta sub 1, sine theta sub 1, cosine theta sub 1. Same thing with theta sub 2. Here. Okay, so multiplying, what do I get here? So I'm going to get a 2 by 2 matrix. What are the entries going to be? So the first entry is going to be cosine of theta sub 1 times cosine of theta sub 2 plus minus sine theta sub 1 sine theta sub 2. So this is minus sine theta sub 1 sine theta sub 2. Okay, so that's in the first slot. In the first row, second column slot, this would be minus cosine theta sub 1 sine theta sub 2 plus, which would also be minus sine theta sub 1 times cosine theta sub 2. Okay, so that's our first row of that matrix. The second row would be sine theta sub 1 cosine theta sub 2 plus cosine theta sub 1 sine theta sub 2. Okay, and then the last one would be minus sine theta sub 1 sine theta sub 2 and plus cosine theta sub 1 cosine theta sub 2. Okay. All right, now you might look at this and say, wait, what am I doing here? But rotation through theta 1 plus theta 2, it's given by the product of these two matrices, but what is it also given by? Right? It also must be given by the basic matrix cosine of theta 1 plus theta 2 minus sine theta 1 plus theta 2 sine theta 1 plus theta 2 and cosine theta 1 plus theta 2. Why? Well, this comes from just the fact that now we've seen that a rotation through an angle theta is given by this matrix involving cosine minus sine, sine, and cosine. So the same thing must be true for these things. But what we can do then is just equate the corresponding entries, since these things must be equal, and the product of these two matrices is equal to this. So what do I get when I do that? So equating the corresponding entries, I get that cosine of theta 1 plus theta 2 is equal to cosine of theta 1 cosine of theta 2 minus sine theta 1 sine theta 2. And I get sine of theta 1 plus theta 2 is equal to sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2, which are the two familiar formulas for angle sums for sine and cosine. So there's an even better proof that's more or less equivalent to this that we're going to see here in a second. But this is one proof of using matrices in this way. Now, this isn't the only way, or this isn't the only benefit you get from using matrices. In fact, what is nice about using matrices in this way is this would allow you to define rotations in higher dimensional spaces. So this, when I say this, I mean using matrices, allows us to define easily rotations in Rn. That we're not going to do that here, but you can. Okay, so we won't follow this thread, but this is one thing that you can do. In fact, better than that, we can think of the group. Well, I already spoiled it by saying the word group, but we can think about the group of isometries for Rn as being described by matrices. Okay, so in fact, we can think of all the isometries of Rn, right, as a Euclidean space in terms of matrices. This is a big hint to what comes later, where this isn't just true for the geometry that we've seen up to this point, but if we begin to describe a geometry that is not Euclidean, then what this amounts to is that this isometry group, or this set of isometries, is going to change. Okay, so for Euclidean geometry, this set of all the isometries would be one thing, and it would be there would be different isometries here if we're talking about non-Euclidean geometry. So the importance of this is really that we are seeing the first example of transformation group stuff, which is the final pillar of geometry according to this textbook. So, but for R2, we can also talk about rotations in another convenient way. And that is using complex numbers. Okay, so we can actually use complex numbers here. So let's say that we have a rotation described using the usual rotation matrix. Okay, so let's say that we have a rotation corresponding to multiplication by this matrix. Associate to this business a complex number, cosine theta plus I sine theta. Okay, where I squared is equal to -1. Right? Of course, another way of thinking about this is square root of -1 is I. Okay. All right. And so, think of a point xy in R2 as written like a complex number. So you've seen this in some form before that actually visually, right, before I get into anything too technical, visually, if I ask you to plot the complex numbers, well, like you would plot real numbers on the number line, plotting the complex numbers means you plot them on the plane. Okay, and so an ordered pair in the plane can be identified with a complex number. So the complex number in question, if my coordinates are x, y, the complex number in question is the complex number z that is x plus I, y. Right? So x and y are real numbers. I is this imaginary unit. And this is how I'm going to write my point. And so, thus, rotation of a point xy through an angle theta about the origin is given by multiplying by this complex number cosine theta plus I sine theta. So this is cosine theta plus I sine theta times x plus IY. Okay. What do I get? I get, when I multiply this, I have x cosine theta. I have x times cosine theta here I would have iy times I sine theta, and I times I is minus 1. So I would have minus y times sine theta, right, plus I times everything else here that I'm going to get. So I would have the mixed term I times x sine theta, so that's x sine theta, okay, plus y cosine theta. Okay, so this would be me rotating the point x, y through an angle theta about 0 by multiplying by this complex number cosine theta plus I sine theta. But notice what happens, right? Notice what happens when I do this. So if I were to write this as an ordered pair, what ordered pair would this be? So it would be the ordered pair x cosine theta minus y sine theta, and in the second slot would be x sine theta plus y cosine theta. Now you can either notice that this is the exact same generic vector you get when multiplying by this matrix, or even going back to the thing we did before, if I replace cosine theta with c and sine theta with s, what do I get here? I get cx minus sy in the first slot, and in the second slot I would get sx plus cy. Oh hey, that's exactly, r sub cs of xy, right? Okay, and so this is another way, multiplying by a complex number cosine theta plus I sine theta is another way of thinking about rotation. And so I can do this proof one more way now. So then rotating, thus rotating xy through, say, theta sub 1 plus theta sub 2 is multiplying by the number cosine of theta sub 1 plus theta sub 2 plus I sine of theta sub 1 plus theta sub 2. Okay. But also, it is the same as the product so whatever this effect is the same as the product cosine theta sub 1 plus I sine theta sub 1 times cosine theta sub 2 plus I sine theta sub 2. Why? Well, because we know how rotation should work, right? If I have a means to describe a single rotation through an angle sum, that should be doable in this single multiplication as I described on the previous page. Since I could do that, I could form this for any angle theta, even if theta arises as a sum of two smaller angles, right? That's fine. But also, there's nothing wrong with me rotating by part of it and then rotating by the second part, right? And so that would be two successive multiplications done in this way. So this is a product. What is that product equal to? So that product is equal to, let's just multiply this out and simplify. This product then is cosine theta sub 1 cosine theta sub 2 minus sine theta sub 1 sine theta sub 2, okay, plus I times cosine theta sub 1 sine theta sub 2 plus sine theta sub 1 cosine theta sub 2. Right? But line these up. These have to equal cosine theta sub 1 plus theta sub 2 plus I times sine of theta sub 1 plus theta sub 2. So matching these yields another proof, an even easier proof. So it yields another proof of cosine and sine angle sum formulas. Right? Since these two things have to match up, and so do these. Okay. All right. So this is an example of how the algebra we've developed in these last couple of chapters can be used to get a lot of the things that you're familiar with already from geometry in a pretty painless way, right? This is relatively painless. This was literally some very basic algebra that I had to do in order to see this. So I just had to carefully think about what those quantities were doing, and then I was good. Okay, so there is the following discussion. So recall from chapter 2, so Hilbert's axioms needed 20, or actually I needed 17. You could make do with 16 if you didn't care about completeness. If you really wanted to just reproduce the plane in such a way that if you really just wanted to mimic what Euclid did in the elements, if all you cared about was setting up a system that allowed you to produce every single theorem that Euclid proved in the elements, then you were fine with 16 axioms. 17 axioms gave you a plane, R2, that was identical to, or it gave you a plane that was identical to R2, I should say. So it needed 17 axioms. If we approach via vector spaces, we need 20 plus axioms. Okay, so quickly to show you what some of these are. So the axioms in question, you had the vector space axioms themselves. There were 8 of those. Okay, then you had the axioms concerning the inner product. So you needed some structure. You needed a sum, and you need scalar multiplication. Right, so those were tied in to these vector space axioms. You needed an inner product on the space that gave you the notion of distance, and then followed from that angle and everything. So so you needed these inner product axioms, and of course what's related to that is like the cosine formula. But then for the scalars that you're using, you needed some basic facts like what are called the field axioms. So these scalars had to live in, the scalars weren't allowed to live in some more general space. They had to live in something called a field, which is a very, very nice and very restricted, rigid space. So altogether, that's about 20 plus of those axioms. Now, it's not that big of a deal because these axioms, vector space axioms, field axioms, these are axioms that stating those or having those at the ready is useful for various other in various other fields and various other disciplines. Whereas the Hilbert's axioms for geometry that we saw at the end of chapter 2, this was mostly only useful specifically in geometry. And so these 20 plus axioms in some way are more convenient than this list of 17, but still it's a lot of axioms. Either way you go, there's a lot of axioms that are assumed here. So the idea is, can we discuss geometry where we massively scale back the number of axioms. So massively scale down the number of axioms. And the answer, yes. And the result, or a result when you do this, is projective geometry. Okay. All right. Which is our third pillar of geometry? Okay, so remember, this textbook is called The Four Pillars of Geometry. So what are the pillars? The first pillar is compass and straight edge constructions. All right, that's what we did in chapters 1 and 2. The second pillar is what we just finished, which is linear algebra specifically. So it is the things that give you access to coordinates, being able to compute with coordinates, being able to introduce vectors in the linear algebra sense, and matrices. Okay. Of course, there's a lot more we could have done with matrices that we didn't do because we have other things to cover. But this is what the second pillar was, and then the third pillar is projective geometry, which is what we're about to discuss now. So the third pillar. Projective geometry. Now, it wasn't realized until very, very late. So, keep in mind, ancient Greeks were doing this 2,300 plus years ago. The shift in viewpoints here to recognizing that projective geometry was something very, very important that actually contained the geometry they were studying inside of it somewhere wasn't until much, much later. So in fact, this in that specific manner, it wasn't fully realized until the end of the 1800s, almost the 1900s, is when this was realized. So more than 2,000 years it took to realize this. In fact, the place where projective geometry, or noticing projective geometry, initially arose was not math. It was from a very strange place that is maybe unexpected. So it came from art. So art is actually where the initial investigations into projective geometry came in, and it came through the notion of perspective. Okay, so perspective is where projective geometry arises. And the strange thing about this, right, is you're used to maybe some things from physics or maybe computer science or something making their way backwards into math as some kind of application to some mathematical discipline, but you're not used to art having too much to do with math applications. So the question is, in our first pillar discussion, we were doing compass and straight edge constructions. Okay. Now, I said on that last sheet that I want to talk about a type of geometry, or I want to see, rather, what happens to my discussions of geometry if I significantly relax that list of axioms. So if I take that list of axioms and I try to scale it back to make it very, very minimal, I want to see what happens. Okay, and so one way of thinking about that is, what happens if I get rid of the compass Okay, and instead of doing compass and straight edge constructions, I just do straight edge constructions. So, question, is there anything of note that I can construct using only a straight edge? Well, remember, when we talk about a straight edge, we don't actually have these markings, right? So our straight edge is completely unmarked. So the straight edge is really used as a method of extending lines. Okay, so drawing in lines, extending lines between 2 points. That's what we use a straight edge for. And so when I'm using only a straight edge, note, I will be completely unable to draw equilateral triangles, squares. So I won't be able to draw equilateral triangles, squares, any figure involving equal line segments. Why? Well, because the compass is what's used to transfer lengths, right? So the compass is what's used to measure lengths. And without this ability to measure, compare lengths, how could I say that two lengths drawn are comparable? I can't, right? Because this straight edge doesn't, it's not a measuring tool, so I can only draw stuff with it. I can't actually measure. And so I can't actually construct any of these basic things, right? Equilateral triangle is literally like the first thing we constructed, right? Day one of class, we constructed the equilateral triangle. So if I can't do that, right? If I can't draw these very basic things, then what can I hope to draw? It turns out, yes, I can draw something of note. Now, what's your definition of note? Of course, I can draw lines. That's what the straight edge is for. But actually, I can draw a perspective view of a tiled floor. Okay, what does that mean? All right, so let's bring this closer. Okay, so here's a perspective view of a tiled floor. All right, so this was drawn just with straight edge. Okay, so straight edge alone is enough to draw this thing. What does this thing look like? All right, when you glance at this, what's your first feeling? Your first feeling, you have an intuition. Your intuition tells you this is clearly a depiction of a floor with tiles, and all of the tiles are the same size. But isn't that really strange? Because think about it. If we actually measured these things, of course they're not the same size, right? I tried to measure, there's this tile as drawn looks like this, and this tile, of course, is much smaller, right? And yet, the way that we see it, this tile, which is clearly bigger in an absolute sense than the ones next to it, but the way that it looks is that it looks equal, right? These tiles look like they are the same size. So that's really weird, right? That we have the notion of looking, right? How a thing looks, not how it is. Because if we bring out our, measuring stick now, so now we have a measuring stick, not just a straight edge, and I were to measure these tiles, obviously, these tiles are getting smaller as they're approaching this edge here, right? They're obviously getting smaller, and yet our mind tells us that all of these look like they're the same size. Hmm. So what is going on? I mean, what is going on with that picture? What is going on? Well, I can use straight edge alone to draw figures that look equal, right? But not figures that are actually equal, right? So, what is this telling you? So I said I can't draw equilateral triangles. I can't draw squares. I can't draw regular hexagons. Okay, I can't draw those things using just a straight edge. Okay, because they require me to construct line segments of equal length, and I can't do that without the compass. Okay, but what's weird is that, and a little bit mysterious, is that I can't draw figures that are actually equal, but I can draw figures that look equal. Okay, and what does it mean to look equal, right? That's something that we haven't really talked about, right? Because this seems very mysterious, that our eyes look at a two-dimensional drawing and then I I see something, right, that is not really there, right? I am seeing these tiles like approaching the distance, approaching the horizon, right? And also note that one of the very, most important things here is that it seems in my mind's eye when I look at this, it looks like, say, for instance, this edge and this line are parallel, right? It looks like they're parallel. It looks like this row of tiles goes on forever, and that this edge is never going to meet up with that other edge out here. That's what it looks like. So it actually looks like, if I look at this, it looks like these two lines are parallel in my perspective. But we know that they're not parallel, right? You can clearly tell that this, if I were to take my straight edge and extend this line segment as a line and do the same thing here, we would clearly see that these things intersect. Right? So they're certainly not parallel in the absolute sense, but it looks like they're parallel. That's a really strange thing. So this is perspective drawing. And this first glimpse into projective geometry came originally from artists in the 1400s. It came originally from 15th century artists, mostly in Italy. In fact, it might have originated entirely in Italy. Okay. So this is definitely a fun thing because, like I said, it's not every day you get to see, or you get to say that artists were the inspiration behind some field of math. But here, for instance, let's look at some before and afters. Okay, so let me bring up a picture before. So here is a drawing from the 1400s. This is The Birth of St. Edmund by an unknown artist. So here's a drawing. It is from England. So even though it's in the late 1400s, this is from England, where apparently they didn't know about perspective yet. And what do you notice? Well, you might look at it and say, if we're interpreting this viewpoint, right, as us looking into a room, right, so the viewer looking into a room, then this looks off. Like, this looks really off. Like, look at how the room is laid out. It's not clear at what height we are. Are we looking straight into the room? Is this bed flat? How is any of this, the way that this is drawn, especially if you look at the directions of the tiles on the floor, it doesn't make a whole lot of sense. right? So looking at this and looking at, what height are we at, what angle are we at? Like if we're looking into a room, this just looks all odd. It just doesn't look right, right? Like from this angle, we're able to see way too much behind the bed, for instance. Unless there's some like dip in the floor or something, this just looks strange. So one of the easiest ways that you can tell a perspective, whether or not the artist has utilized perspective drawing, is say things like tiles, right? So look at the tiles on the floor, right? So we're viewing this at an angle, and yet the floor is the tiles are perfectly rectangular, right? They're rectangles from our view, right, at every angle, which is part of what's throwing us off here and trying, this is making everything look just totally non-realistic. Forget about everything else. I'm just talking about the perspective now, right? So if I look at these tiles here, all these are rectangles, right? Even though if you have a tiled floor in your house, if you look down at the tiled floor and then you move around the room and keep looking down the tiled floor, it doesn't look right. It doesn't look like you've just drawn it projected down, like looking straight down on it, right? You don't look. It doesn't look like that at all. Okay. Okay. And so this is a not drawn in proper perspective drawing. So this does not utilize perspective drawing. So let's look at one that does. Okay. So this is by Albrecht Dürer. So this is St. Jerome in his study. And note the difference here. So we're looking into a room. Looking into this room, it is clear that what angle and what height we're looking in from, and everything looks realistic. Everything looks the way that it would if you were actually looking into a room. So what do I mean by that? Notice that, so he's sitting at a table or a desk here, okay, and the top of the table, right, the table surface, which we would know would be a rectangle of some kind, right, is drawn in such a way, look how it's drawn, right? We know that it's a rectangle, but it's drawn in such a way that if you were to actually take a pencil and trace the outlines, it's drawn as some kind of weird trapezoid thing, right? It's drawn as some kind of weird trapezoid looking thing because of the perspective. The point is that it is drawn this way, okay, to create the illusion of depth here, right? And you can look at the ceiling, you can look at the boards in the ceiling, you can look at any number of things to show here that this is some trickery has been done, right, to give the illusion of depth. And you can see how much more realistic it looks when you do this. Okay, so this the method that Italians used to draw tiles was called the costruzione legittima. Yeah, so the legitimate construction. So the Italians drew tiled floors via the legitimate construction. So, costruzione legittima. I don't know that I'm pronouncing that right. So what is this construction that they use to create this illusion of a tiled floor? Well, the idea is you have, say, you can construct it as a rectangle first if you really wanted to. The idea here is that you started with a line at the bottom of equidistant points. So you might have objections here, and I'll talk about that in a second, or actually not today, but I'll talk about it next time. So at the bottom of this segment, you have equally spaced points. Okay, so then what you do is you select, say, a point here on the horizon, okay, and you connect those equally spaced points to that point, okay, and then what you would do here is, so what's the horizon? First of all, the horizon is a choice of another horizontal line, that is, it's parallel to the base here. So I have another horizontal line. I can choose a point as my horizon point that all these things are going to converge to in a way. And then I can choose another parallel line here in order to draw my first row of tiles. Okay, so when I draw another line that is parallel to my base, I get my first row of tiles. But then the question becomes, if you can't just slap in another horizontal line here, these tiles would look all wrong. They wouldn't be the right size. So how do I make this construction give me a bunch of tiles that look the proper size? I can draw, using straight edge alone, I can draw the diagonal, say from this point to this point, and extend it all the way to the horizon. And let's see if you can see this up close. So that has been done here. Okay, so once that diagonal has been drawn, it intersects all those lines on this side. It intersects all those lines, which gives me intersection points, and I can draw the subsequent horizontal lines that make this tiling proper. So now it really looks like a tiled floor off to the horizon, right? So this is how the Italians did it. So we'll see that this is a little, this actually utilizes some Euclidean geometry, and we are going to do this or replicate this using truly just the straight edge alone. So this really mostly uses just the straight edge, but there's some hidden Euclidean things in there, namely those equidistant points we started out with. So anyway, I'll continue on there next time. So on Friday, I'll continue on there. Yeah, so that's it. We've started chapter 5, so I'll see you all on Friday.